This exercise will help us to understand part of what's stated in the definition of a limit. What we have here is a graph of a function in blue that has a little hole here and a point up there. And you can see on the y-axis, there's a point of interest that's 2, and we're looking at a band essentially that goes from 1.5 to 2.5. And in that band right there, what we have is that the absolute value of f of x minus 2 is less than 1/2. So you may remember that from the definition of a limit as f of x minus L being less than epsilon. We'll come back to that in just a minute. Now on the x-axis, what we have is a point of interest where x is equal to 3. And what we see over here is an inequality. The absolute value of x minus 3 is between 0 and delta, and those are strict inequalities. And this is the part of the definition of a limit where we have x minus a in absolute value is positive and less than delta. I'm actually going to start with the fact that the absolute value is strictly greater than 0. What that means is that for the definition of a limit, x does not equal a. Because if x equaled a, then x minus a would be 0. This is the part of the definition of a limit that allows us not to care that we have a point way up here above where the rest of the function is. Now, as you may recall, in the definition of a limit, we say that the limit as x approaches a of f of x is equal to L if for every epsilon greater than 0, there exists a delta such that if x is close to a, then f of x is close to L. That's essentially what that says. I want to focus on this part where it says for every epsilon there exists a delta. See over here, what we are told essentially with this absolute value of f of x minus 2 is less than 0.5, we're being told that epsilon is equal to 1/2. So that's what these red lines or segments are indicating, that we want outputs that are in the interval from from 1.5 to 2.5. Now I'm going to really nitpick what this says here. We want to find a number delta. Since our point of interest is where x is equal to 3, what I'm looking for is I want to be to the left and to the right of 3 to create an interval over which the output values are between -1, I don't know why I keep saying negative. We want to be in an interval around 3 on the x-axis. So the output values are between 1.5 and 2.5. We could say, hey, the interval is from 2.6 to 3.8, no big deal. Here's the problem. The distance between 2.6 and 3 is 4/10, right, 0.4. The distance between 3 and 3.8 is 8/10, right, 0.8. That's two different numbers. What I want is a single interval where 3 is in the middle. And if 3 is going to be in the middle, then whatever I have going on the left and on the right, I want that to be the same distance away from 3. So my choices are basically 8/10 and 4/10, right? Suppose I pick 8/10. I would then be trying to make the statement that if x is within 8/10 of 3, then all the output values associated with those input values are going to be between 1.5 and 2.5. And here's where the problem is going to be. If I go 8/10 to the left and to the right, then I'm going to end up with input values such that their output value is not between 1.5 and 2.5, right? So in other words, if 3 is going to be in the middle of my interval, the exact center of my interval, then 8/10 is too big. So let me get rid of that. That leaves us with the option of 4/10. If my interval is 4/10 wide, so 4/10 to the left of 3 and 4/10 to the right of 3, then I am guaranteed that the output values for all of those x values are going to be between 1.5 and 2.5. And we might think, well, look, I'm missing some output values over here and some input values over there. It doesn't matter. What I'm after is a single number delta such that if x is within delta of 3, then my output values aren't going to be outside of the region that I've already defined. So for epsilon equaling 1/2, my delta is going to be 4/10. In a situation like this, whenever I have an asymmetrical interval that satisfies the output criteria that I'm looking for, I'm always going to go for the smaller of the two radii, or the smaller of the two distances. Now, the definition of a limit says if for every epsilon greater than 0, there exists a delta such that as long as I have a delta neighborhood, then my function is within an epsilon neighborhood. The focus is for every epsilon. So suppose we zoom in a bit, and instead of from 1.5, oh, we've already answered the question, and now I'm just exploring more. Instead of going from 1.5 to 2.5, suppose I change this and I say, I want the outputs to be between 1.9 and 2.1. Will I be able to find a delta neighborhood that makes that happen? And the answer is yes. It looks like that would be the size of my delta neighborhood, right? And I can snug this up and be as small as I want over here for epsilon, and I'm always going to be able to find a neighborhood about 3 that will be such that any of those input values will give me output values between the two numbers that I've specified. So that's how this relates to the definition of a limit.